Okay, so we are going to finish discussing hydrocarbons, and we are going to focus on what happens when you have at least one double bond and at least one triple bond. We are going to change the ending to ENE. Again, there is the general formula. We're not really going to focus too much on that because we're going to do the same thing. We're going to name and we're going to draw and we're going to show how the atoms are arranged. So we are going to follow the same rules as alkanes. So number 1, longest chain. And then number 2, you're going to use the lowest number. To label where the double bond is. Okay, so just like we did with when we added stuff to the chain that only had single bonds. And as we did before, you could have 2 double bonds, which then you would use di for, and tri would be 3. But again, the numbering is more important here so that we can say where on the double chain, the parent chain are the double bonds. All right, so let's do some practice. So we'll do the same thing. We'll name and we'll draw. And so all of the things that we did with alkanes, you can do with alkenes, and then in a second when we do triple bonds, with alkynes as well. So you can have cyclic, you can have straight chains, you can have branches, you can add chlorines, you can do lots of different things. Okay?
Yeah,
I'm making a video. What's that?
You're gonna come up. Okay.
Okay, so in the first chain, we have to find or count what is the longest chain, just as we've been doing before. So whether you go from left to right or right to left, you're going to get 5. This is a straight chain, 1, 2, 3, 4, 5. And then again, don't write this down, but you want to count the lowest number. So you're not going to count from this way, 1, 2, 3, because the double bond would be on carbon 3. Whereas if you go from the left, 1, 2, that carbon number 2 has a double bond attached to it. So we are going to use 2 pentene as the name. So just as we did before, 5 carbons equals pent. And then ENE, because there's at least 1 double bond. And where is the double bond? It's on carbon number 2. So then in B, that's a cyclo, and it's 4 carbons, so it's bute. And again, when you have ones like this, you might see this actually written as cyclobutene because there's 1 double bond, but there is no beginning and no end. So no matter which way you write this, it is on, we would consider it to be carbon 1. So this would be cyclobutene as well, if I drew a better square. There we go. But as I said when we did rings before, if you would like to use the 1 so that they always look the same, then you could definitely do that. Okay? So when you will also be asked to draw. So just like before, sometimes students prefer to draw because then you get to choose. Okay, so again, I encourage you now to go to the end. It's a bute. Okay, and it says on carbon number 1, there's an ENE. So decide which way you're going to count. I'm just going to continue to do left to right. So there's my double bond. And now I've used this as 1, 2, 3. So then on carbon 3, I'm going to put a methyl. So whether you put the methyl in the top of the chain or on the bottom, that doesn't matter. If you like to do your branches as condensed, that doesn't matter. That's great. If you would rather draw it with ticks, that's fine too. Okay. All of those are similar. You just want to show carbon with 4 bonds. So I need to go in and make sure this one has 2 now, carbon 1. So I'm going to put in 2 ticks. Carbon 2 actually has 3, 1 on the right and 2 on the left, which means it only needs 1. Because carbon 3 has a methyl, it only needs 1 in the bottom and then 3 on the outside. Do a better job than I did with my ticks. Okay, so once you start having different endings, then there is another way you can write these. So you might see it written like this. So 3-methyl. And then what people will do, and in a second when we do alkynes, I'm going to show you that there are cases where you have to do this. But you can actually put the number, you can actually put the number exactly where, or exactly in front of the ending. So now this 1 goes right in front of the ene because it's describing where the ene is. But for now, when there is only one ending, either the blue name or the red name, it doesn't matter. Okay, but when we do alkynes, you'll see that you might have to choose, or might have to do both endings. So now when you have a triple bond, then we're going to use the ending YNE. So now we have at least one triple bond. That makes these unsaturated because now you can break those double bonds or triple bonds and make double and make single and add more atoms to the carbon chain. I think we forgot to write that up here. I forgot to write that. Okay, so alkenes are also unsaturated because again, you can change the double bond into single bonds. Okay, so alkenes, it says it right there. Alkenes and alkynes are more reactive than alkanes. If you want to add more here, you can. We will do a whole lesson on reactions, but the reason is these bonds can be broken and changed into single bonds. By adding atoms. Okay. So that's why alkanes, we kind of consider the bottom. They are, to break those bonds, it takes a lot of energy. So we say that they are not very reactive at all. Okay, so let's do some practice. So because alkynes are triple bonds, then you really actually need a minimum of 3 carbons, or sorry, a minimum of 2 carbons so that you can have the triple bond. And so these are often pretty straightforward as well. The triple bond and the double bond really will always be a part of the parent chain. So you can actually use that as a way to sort of help you with your answer. And for the second example here, we're going to do one that has both double and triple bonds, and I'll show you how to deal with that. Okay, so the first one, again, count the carbons, 1, 2, 3, that's prop. Now that we have at least one triple bond, you get the ending YNE, and it's on carbon number 1, so 1 propyne. Or if you like the other way, you could name it like this. Because in this case here, in number 2, you definitely have to do that. We have a YNE here, and we have an ENE, an ene. So we're going to have to use 2 endings. And you still are following the same rules. Count the longest chain. So in this case, that is not too hard to see. 1, 2, 3, 4, 5 is pent. There's no branches. We just need to decide which way to count. So again, if you take a look at this molecule and you look where it's busy, it's busier on the left. So there's a triple bond on the left, and then on the 3rd carbon, there's a double bond. So it's likely you're going to count right to left. If you went the other way, this would be 1, this would be 2. So the double bond would be on 2, and the triple bond, we would say, is on 4. So that is definitely not as low as 1 and 3. So still checking that you're always using the lowest number. So now this time you could do one of them. So you could do, say, 3 pentene, 1 ine. But most people would prefer to do ene, ine. And again, even though it looks weird, there is an advantage because the number goes right with the thing you're describing. The ene is on carbon 3, the ine is on carbon 1. Now, one thing that I don't take marks off for, but I can't guarantee your organic prof will not, is alphabetical order. So here I put ene before ine because it's alphabetical. But if you put pent 1 ine 3 ene, I would not take marks off. Okay, it's more important, do you have the correct number? Do you have the longest chain? The 2 cardinal rules of organic chemistry. Okay, so let's move on and deal with benzene. So aromatic hydrocarbons, they are a structure based on benzene. So you have to have some kind of representation of benzene. So the one on the end here is not condensed at all. So this is showing the alternating double bonds. Which is, it's like skipping. Carbon at the top here, if we call that carbon 1, no double bond. Carbon 2, double bond. 3, no double bond. 4, double bond. 5, no double bond. 6, double bond. So it's alternating. So again, sort of like when we talked about polyatomic ion structures, and I said you can get something called resonance, where the double bonds can kind of move around, which means, so in this last bullet here, electrons that form the double bonds are spread out and shared over the whole molecule. So because chemists, I think, are lazy, then you're most commonly going to see this representation and maybe this one. So what the one in the middle there is trying to represent is that you can have double bonds at really, as long as they're alternating, at different spots in the chain. So instead of trying to number where they go, we call it benzene and we put a ring inside, okay? So a hexagon, like cyclohexane like this, is not benzene. You have to have the ring or the alternating bonds, or you have to draw it out. So one of these 3 representations is a must. Okay, they are very smelly. So again, in the first lesson, we talked about how, the word aroma implies a smell and you think, oh, it's a nice smell. No, it isn't. If I opened benzene in our classroom, you would be shocked because it smells like vomit. Okay, it would make you vomit. It smells so bad. And anything that has benzene will resemble benzene in their chemical behavior. So we consider those to be aromatic hydrocarbons. So they stand out, which even though it's sort of frustrating at first when it's like, it just seems like more rules to remember, it also makes your life a little bit easier because the parent chain is often going to just be written as benzene. And the double bonds are not broken. So the benzene molecule, when we do the organic reaction lesson as well, will look exactly the same. Okay, so it says it's more stable, which implies it's not reactive. Okay? So in a molecule like this, where we have something is, we call it substituted on the ring. So the parent chain is benzene. And then this group is a methyl because it's one carbon. So this is called methylbenzene. And it falls victim to the same ideas as the other cyclic compounds. You often will see it written as methylbenzene because there is no beginning and no end. But if you would like to write in the one, you can. Okay, so it does become a little bit trickier when you have two groups substituted. We call these structural isomers. So these are special, again, because benzene is special. Can't even spell it here. So only for benzene could you use these three. And I don't care which one you use, but you will you'll see both. Okay, so when something is substituted on carbon 1 and carbon 2 in the benzene, then we call that ortho. So this molecule could technically have three names. 1,2 dimethylbenzene. So in this case, all of them are methyls. So you could write 1-methyl, 2-methyl. That's fine too if you forgot about the di, just like we did before, okay? That it's more important about the numbering. But in this case, because benzene is so special, you could also write ortho dimethylbenzene or O, because chemists are lazy, dimethylbenzene. So same thing here, we have carbon 1 and then carbon 3, so we use meta. Oops. Because we always want the lowest number. So we're not going to count to the left and say 1,5. That's not a thing, because we still want to follow the golden rules of organic chemistry. And when you have 1 and carbon 4, then we call that para. Sorry, I'm squishing. Okay. And this is, again, one of those things that you just kind of have to memorize. So if you like flashcards in organic chemistry, you might find that to be helpful. Because benzene is so stable and unfortunately found in kind of a lot of things, there are plenty of common names. So this is called phenol, and phenol is used as a preservative it's in my insulin, it's in medication. So, but really, we try to limit how much there is. Styrene. So if you had many, many of these molecules together, you would get polystyrene, which is styrofoam. Another common one is TNT, trinitrotoluene. And actually the original example, the first one I had that said just the CH3, that's called toluene. So these are just FYI, okay? So let's just do another example here where it's two different things this time. So now you have a bromo and a chloro. So again, this is carbon 1 and this is carbon 4 in the ring. So you could call this 1,4-bromochlorobenzene. And it doesn't matter which one's the 1 and which one's the 4. So you could write 1-bromo-4-chlorobenzene. You could write para-bromochlorobenzene. So as much as seems frustrating to have to memorize something else, benzene is so unique, it stands out so much that you know, it kind of stands apart. So then it stands apart on your page, you know, it's really obvious when you take a look at a question. Now, what happens in the rare case where you have a benzene ring that is long, or a parent chain is longer than benzene? So here we have hept, which is 7. So this is the parent chain now because it's longer than benzene. Oops, I forgot that. Sorry. Okay, and then it's got YL, just like all of our other branches. So now the benzene ring is considered to be the branch. Where is the branch? It's on carbon 2. Your textbook might you might see this as well. So benzyl, and this maybe makes more sense because now you're just dropping the ending of benzene and adding YL, just like we would have done for the other branches. So you can use this interchangeably. 2-benzyl heptane. You can, either of these is fine. This one or the 2-benzyl heptane, either of those is the same molecule. Maybe phenol is a bit more old school, so you might find more, if you look at more modern sources, they use the word benzyl. Okay, so that's it for this. Now you can do all of this homework that's listed and give it a try, especially page 22, because then they'll be all mixed together. One of the questions asks you to fix a name, like there's something wrong with the molecule and it wants you to fix the name of it. So that's a different kind of question, kind of a neat one. So you can take a look at that. Okay, thank you.